Hope your minds are rested. So yesterday we have looked at the Wilson loop as a way to characterize, in particular, crystalline topological systems, but really all topological systems from a bulk perspective, and how to use it to relate to boundary states and topological invariants. And today I really want to walk you through some simple examples to illustrate concepts like topological crystalline insulators, higher order topology, stable versus fragile versus delicate topological phases. Before doing so, I wanted to quickly, and that's actually a nice recap from yesterday, catch up on a question that was asked about the relation between the Chern number, Wilson loop flow, and symmetries in a case, for instance, where we have inversion symmetry. So that's just a parenthesis. So the real part of the lecture will start in 2 minutes after I answered this. So let's consider we have a Chern insulator, and it has the following, and it has inversion symmetry. Inversion. What is that? And the occupied band. So the key signature is the inversion eigenvalues of the occupied band at the inversion symmetric momenta. So if we have the Brillouin zone, and the inversion eigenvalues are like so, then the Chern number is odd. That's something we know from theorems, but the question I guess was, can we also interpret this, or can we relate this to the Wilson loop spectrum? And actually we can. So what we can do is we can look at the Wilson loop spectrum for Wilson loops along the y direction, for instance. So these kind of Wilson loops, and plot the spectrum for each of them. And let's see how they're supposed to look. So so that's as a function of kx, and this direction would be the Wilson loop eigenvalue theta. And let's say there's only one occupied band, so that all of this is also periodic, from minus pi to pi in x, and also from minus pi to pi in the theta direction. And what I would like to appeal to is knowledge from the SSH model, which you might or might not have. But in principle, these cuts that I highlighted here, that these red cuts, you can understand them as at least the inversion symmetric ones, so the one at 0 and the one at pi momentum, as SSH models. And we compute their Wilson loops, and we know that by inversion symmetry, they are quantized to be 0 or pi, the polarization, right? What Jen was mentioning. So in this case where we have 2+ eigenvalues, there's no band inversion, if you wish, or no inversion of the eigenvalue. That's the trivial phase of the SSH model, and the eigenvalue, or the polarization, will be 0. And then this is the one at pi is the interesting topological one, and the eigenvalue by inversion symmetry is pinned to pi. And now you have to complete this in an inversion symmetric way if the whole system is inversion symmetric. So that you remember theta of k is equal to minus theta of minus k by inversion symmetry inversion, or C2, and there you go. That's how you can basically deduce that if you have this type of pattern of inversion eigenvalues, there's no way of getting no Chern number. Yeah. So this is the only way I can draw this line topologically. It has to wind if I have inversion symmetry. In particular, let's say somebody came up with the idea of drawing this line, which would be periodic. It would, that requirement would be met. It would also go through the red dots, but it does not meet this requirement. So it would not be an inversion symmetric flow of the Wilson loop eigenvalue. So we've basically shown now using this Wilson loop argument, we've shown this relation that the Chern number is odd if you have such a pattern an odd number of inversion eigenvalues which are -1. All right, so that was just a little addition or a little sort of 101 addition to what we did yesterday. But now we want to really go to topological crystalline insulators.
Titus?
Yes.
There is a question in the Q&A.
Is the shape of the path of the eigenvalues important for any physical observable? I mean, that was a similar question yesterday, and I mean, in a sense, yes. It is an observable. It's gauge invariant. You can measure this in some way if you make a plane wave excitation in x direction, with a specific kx, and you measure the polarization that you get out of this plane wave traveling in the x direction in the y polarization. This is precisely what you would measure, but it's not an easily accessible observable, and certainly not a topologically protected one. So you can change this smoothly with changes in the Hamiltonian. So the answer is yes, it's an observable. Can measure it in principle, you can probably design it, but it's not something that experimentalists would like just like the conductivity or something that would be easily accessible. Yeah. All right. Thanks. Okay, good. So what we want to do is basically a tenfold way plus crystal symmetries, and there was in Jen's talk the question about the chiral symmetry, and this is actually my first example of a topological crystalline insulator that would be in class A3 plus a mirror symmetry. So if you might not remember what all these classes are, class A3 is the class that has only chiral symmetry, and in 2D, class A3 does not have a non-trivial phase. But what we want to show is that when we also consider a mirror symmetry, we can make it non-trivial. And so this thing has chiral symmetry. And chiral symmetry is defined as C on H of K, C inverse, where C is a unitary operator, is minus H of K as well, same K. The conventional way of dealing with systems with chiral symmetry is to go to the eigenbasis of chiral symmetry, so the place where this is represented by a unit matrix and minus a unit matrix. And in the case that we are going to look at, we want this to be 2 by 2 matrices, so the whole Hamiltonian is going to be 4 by 4. And then the Hamiltonian can be written in this case. Chiral symmetric Hamiltonian can always be written in this form: Q of K, Q dagger of K with some matrix Q, also referring here to Andre's talk where such structures appeared. The specific model that I want to introduce is the following, and I'm just going to introduce it as in K space here. It's straightforward to go back to real space if you are interested in that. But it's more easy to interpret in K space. Sine Ky minus sine Ky. And I'll shortly tell, or it will shortly become clear why I choose this to be minus ikx. Okay, and I say I want this to be mirror symmetric. So what's the mirror symmetry? So first of all, the mirror symmetry acts. I want the mirror symmetry in y direction that acts on the Hamiltonian as follows: my inverse h of kx minus ky, and the specific representation of mirror symmetry that I want to choose here, or that this Hamiltonian obeys, is sigma z 0, 0, sigma z. So simultaneously, I've diagonalized the chiral symmetry and the mirror symmetry. And there are two mirror subspaces, one with +1 and one with -1 eigenvalue. So the observation is now that, so we want to look at the system that is that is open in x direction. And we can keep the periodic boundary conditions in y direction so that the boundary itself is mirror symmetric, and ky is a good quantum number. And in particular, then at ky equal to 0 and pi, I have mirror symmetry in the spectrum. And I can classify the states by mirror eigenvalues plus or minus 1 in this case. And what we see is that at these places, we have a decomposition of this Hamiltonian. So let's go to, for instance, to ky equal to 0. Then we see that these cosine terms are vanishing, and the Hamiltonian just looks e to the e to the ikx, e to the minus ikx, 0, 0, e to the minus ikx, 0, 0 to the ikx. All right, and that should ring a bell. So this Hamiltonian looks particularly simple. It's actually two copies of an SSH chain, yeah, and each copy is happening in a different mirror subspace. So there is one SSH model here, yeah, which has this winding, and there is another SSH model here, and they are in different mirror subspaces. And now I can already, I'm claiming that I can already basically infer now the boundary spectrum of this model just from this knowledge. So I'm going to sketch you as a function of ky, the open boundary condition spectrum of this model, and some bulk bands, and the ky goes from -pi to pi. And at 0, we know we have these two SSH models. We have chiral symmetry, so their boundary states come to lie exactly at 0. And now the question is, how, and also, by the way, if I go to ky equal to pi, then these states turn out to be at ky equal to pi, they are, these terms are 2, or sorry, -2, then we're on the trivial phase of the SSH, so there should not be any boundary mode. So the only question is, how do we extend these modes here? And there are, you know, basically now a bunch of options, but I'm arguing that the only option that's actually feasible is this one. So these two states have to cross the spectrum like this. And the reason is the following. Due to chiral symmetry, I have this spectral symmetry of plus and minus. And due to mirror symmetry, I have a symmetry between kx and minus kx, ky and minus ky. So, so there's really no other way than connecting them in this topological sense with a spectral flow. Specifically, if I was to consider a case without chiral symmetry, then what I could have drawn is something like this, right? Without chiral symmetry, this would be mirror symmetric. You have the double degeneracy here, but there's no topology in the sense that there's no spectral flow across the entire gap. And without mirror, specifically, there is no protection of this double degeneracy at ky equal to 0. So in principle, I could have written a spectrum like this that's still chirally symmetric, but it's not mirror symmetric. I mean, it is not, this mirror protected crossing, yeah, is not there. Notice again the red and the blue. the red and the green state have different mirror eigenvalue. Okay. And a topological invariant, if you want, of such a state is the Wilson loop eigenvalue in the different mirror subspaces subtracted from one another. So we know that basically, maybe I should have, and that is at k y equals to 0. So sorry. So w plus minus w minus, and that all at ky equal to 0. And this thing is going to be yeah, pi, or 2 maybe, it's pi. So they wind non-trivially, but in opposite directions. So the question: what is the real space representation of this model in terms of size and coupling links between them? Yeah, so that, I think that is something one can straightforwardly work out. I just don't feel like doing that now necessarily, because it's going to take us more time than we get out of it. So I suggest that so you see there are only first order harmonics in this, and there are 4 orbitals per side. So you just go and make a square lattice. You have 4 orbitals per side, and then you look. It's only nearest neighbor hopping, but the matrices which these hoppings come with depend on where these harmonics entries are in here. So I encourage you to do this as an exercise yourself. Okay. Sorry for not providing this, but it's just, I think it's just taking us too much time. All right. Thank you. But it's a good question in principle. Now let me go to higher order topology point of view. In this model. So what I want to do is, so far I've looked at the edge that's perfectly mirror symmetric, right? So I have this mirror line, and I have this perfectly straight mirror symmetric edge. Now I want to think about what happens if I consider an edge that's slightly tilted away from this mirror symmetry. So so I want to keep chiral symmetry, but mirror is slightly broken. Then, so for this edge, we know the spectrum is going to look like this with the degeneracy point. And here now we have little mass gap, right? We have this picture because we broke mirror slightly, and there is a Dirac, so it's like a 1D Dirac equation with a mass. And basically now I want to contrast this to tilting it the other way, and I will have the same picture, because the two are kind of mirror related. But if this is a linear order effect, so if this mass is really introduced by linear order in this kind of tilting angle, then going to negative angle, I should have the negative mass. You don't see that in the spectrum of the Dirac equation, but it's still intrinsically there. So and now I need to appeal to some knowledge in Dirac theory, and it's an interesting part to study if you don't know it. If I make a domain wall where on both sides I have a gapped Dirac fermion, but the mass is larger than 0, and on the other side it's less than 0, so it has to go through 0 someplace. Then at this domain wall where it goes through 0, I will find a bound state. Okay, and so this is a bound state. zero-dimensional bound state at domain wall of the 1D Dirac equation. And this bound state is pinned to zero energy because it's the unique state around there by this chiral symmetry. To E equal to 0 by chiral symmetry. Okay, then there is another question. If you cut like this, you could also have trivial surface states from dangling bonds that you cut. In a more complicated spectrum or material, how do you distinguish them from the topological states? Right, that's correct. There could be additional states. They would always come in pairs. So the topological statement here is that there is an odd number. So in particular, you're thinking maybe there's another set of states here. But what I can assure you is that no matter how you cut, there's an odd number of states here, or exactly an odd number of states at zero energy. So it's a very good question. So the spectrum will have one state locally, I mean, of course, somewhere it needs to be gapped, otherwise it's kind of pointless to talk about it. But there's an odd number of states at zero energy, and then you can have like other states pairwise, or even at zero energy, another pair of states. But so that's like my energy direction. That's not really any axis perpendicular to that. So so what is from the bulk topology, what is guaranteed is that there is an odd number of these corner states. And that is actually an important point to make, because the bulk topology here, it actually has to do with winding numbers. So there's actually a set topology in the bulk, but can only tell you about the C2 number of these corner states. So another question, in the quantum spin Hall scenario, they also appear pairwise, right? In the quantum spin Hall case, I guess you are asking about when you have not a single, well, actually, I'm not sure. Is the question about a time reversal symmetric system or a time reversal breaking system? In a time reversal symmetric quantum spin Hall insulator, there's no way to gap the edge modes, so there's no point talking about corner modes. If we break quantum time reversal symmetry, then there can be single corner modes from higher order topology, and then pairwise from dangling bonds. So I'm thinking that's what you mean. Yeah. Okay. Okay, good. Now I wanted to tell you a bit more about mirror numbers, but I think I'm going to skip that in the interest of time and move on to, because also it was something that Jen has already covered, so I don't have to do that again. And it's just to say in words, I mean, we've heard from Jen that there are mirror numbers, which are basically the churn number on a mirror plane in a 3D crystal, where it can decompose your Hilbert space in mirror even at odd states, and you compute the churn number of one of these mirror subspaces. And I just want to add that there's also a higher order topology component to that, namely if you have a hinge of a 3D crystal, and that hinge is mirror symmetric, then if the mirror churn number is 2, for instance, then you have a single helical Kramer's pair of propagating modes on this hinge, and the surfaces are gaps because, again, surfaces like in this example, I would tilt them with respect to the mirror plane so that they can be gapped. Okay, so anyways, that was sort of just a recap from what Jen already told you, and this brings me to section 3 of my talk, fragile and delicate systems. Okay. So basically, the viewpoint here is that of Wannier functions, and topology is in this point of view. Topology is defined as an obstruction to Wannier localize, to exponentially localize symmetric Wannier states. So topology is an obstruction to exponentially localize symmetric Wannier states. Except for the Chern insulator, you can always exponentially localize Wannier states if you don't care about extra symmetries. But if you want the Wannier states also to satisfy, for instance, time reversal or spatial symmetries, then you get this characterization of topology. Okay, and then strong topology if this obstruction persists upon the addition of trivial orbitals, i.e. atomic limits to the occupied bands. And then fragile topology is if the obstruction is trivialized by this. Okay. And now let's give an example. It's a simple one for this fragile case, because that may be a bit, maybe still a bit dubious to some. So, and again, I want to use basically the Wilson loop perspective. So it's in 2D and a very simple case. So I want two Chern insulators. Insulators with C equal to 1 and -1, so with opposite Chern numbers, and I want to superimpose them. And now I have to tell you what symmetries I care about. So if I decouple these two systems, I can think of having time reversal symmetry. So I could have a quantum spin Hall type system, but actually I don't really care about time reversal symmetry. Instead, I impose this combination C2T, C2ZT that Andre already mentioned extensively in his talk. So we have a C2 symmetry. So these Chern insulators are 2D systems. We have the C2 symmetry that rotates. So it's like inversion in 2D, roughly speaking. Okay, so what do we know about this this example in terms of the band structure or the Wilson loop perspective? So first of all, just so that we have a picture in mind, so the energy bands, there would be basically one set of bands from so there's two occupied, two empty bands where the Chern number is -1 in the occupied and 1 in the unoccupied space, and then we have another set of bands, actually just one band, but I'm kind of putting all the k in one place here. So there the Chern number is -1 upstairs and +1 downstairs. And now I want to compute the Wilson loop for these the bands together, and what would that look like? Oops, I get the Wilson loop spectrum as a function of one momentum. I don't really care which one I choose. these are the theta values. It looks like so, and then I get, let's say, one mode that goes like this from one set of bands, and the other mode goes like this from the other set of bands if they are not talking to each other. And now the question is basically, if they talk to each other, can I open a gap? And the claim that I have is that this degeneracy point, both at Wilson loop eigenvalue 0 and pi, is protected by a C2T symmetry. Let's see, protected by C2T, and let me show you that quickly. So that is at theta equal to 0 or pi. And the simplest way to show that, there's a much more mathematical, is this Kane-Meilei. You can use Kane-Meilei if you, with 0 rush bar. Well, I mean, since I'm saying specifically that I start with this Chiral number plus and minus 1, then you maybe want to choose Kane-Meilei with 0 rush bar. So that would be a possible model to use, yeah. And then, but you don't care about T, but you put perturbations that are C2T symmetric. So how do we prove? First of all, let me remind you, C2T squared is equal to +1 in this case, even though we have spinful electrons in mind in principle, but the -1s from T and C2, they multiply to +1 here. So the proof, let's say, my proof is super simple. There are more mathematical ways to approach this, but I really don't want to scare you. So we have this, let's say, Kx Wilson loop, and we remember it's an operator. So let's go to, say, K around one of these degeneracy points, and I claim that this Wilson loop, or obviously in the eigenbasis of the Wilson loop, it can be written like this. Miguel, I'll get to your question in just a moment. I'll just finish this proof. And now, what can I use for C2T for the representation? Obviously, it has to be complex conjugation because it's a time reversal operator. And sorry, I wanted to do sigma z here. This is a typo. Sigma z in the eigenbasis. So here I claim I can only put sigma x. Why can I only put sigma x? If I had put sigma y, then it would square to -1. And if I had put sigma z, then it would not do the right thing together with this Wilson loop, because it should, it should basically turn the Wilson loop into minus itself, right? So this is the only choice I can make. And now I can ask, what is, if I perturb this Wilson loop, what is the possible perturbations that I can put? So I start with Kx sigma z. Now I want to put the mass term potentially, yeah? Sigma x mx plus sigma y my plus sigma z mz. But of course I want C2T of W of Kx, or W tilde of Kx, and C2T inverse. I want this to be minus W tilde of Kx. And you remember that was the transformation property of the Wilson loop that we had noted yesterday for C2T symmetric systems. And now if I actually compute what I have, I get minus Kx sigma z, and then I get plus sigma x mx plus sigma y my minus sigma z mz. And that tells us that mx and my have to be equal to 0 for this to be satisfied. And so the Wilson loop cannot be gapped. I can have a MZ, that's okay. But what will that do? It will just move this degeneracy point around in the k direction, but it will not remove it. It's pinned to k to 0 pi eigenvalue. Okay, so now let's go back to Miguel's question. How if you add to the fragile bands other atomic linears that cross with the fragile topological ones only at theta equal to 0 or pi that are protected by C2T? The crossing should be protected and the one-year obstruction should remain intact, despite the fact that you are adding trivial bands. I see what you mean. So you want to put, so you are already anticipating what I'm going to say next. I'm going to say, well, we can add a band here or there, and then I can gap them out like this. And so the flow that I just produced, and that's protected as long as you only have these two bands, only the red and the green one, is then gone, right? So it's only protected until you add these bands. I think what you cannot do is add a single band to this manifold that is pinned to 0 or pi. So because you want to do this, right? You want to add a band like this. I am trying to see how I can prove that. I think one would have to go back to the Hamiltonian and the representation of these states. So if you allow me to reinstate time reversal symmetry, then I cannot do that because I can only add Kramer's pairs. But that might not be super satisfying because afterwards I'm just breaking this this time reversal and only keep C2T. Yeah, so the whole point, what I've shown here basically is that these states, if I take this state that's pinned to 0 or pi, there needs to be another orthogonal state with the same Wilson loop eigenvalue. And such a flat band that you propose, if it's not degenerate, would break this rule. But I think the actual way to show it is a bit more mathematically involved. If you want, I can dig the reference out for you and put it in the Slack. I would say that's probably the most efficient way to go about this now. Okay, good. But thanks for the question. It's very, very good. Yeah. So we have this fragile topology, and I just want to mention also that there's also a higher order topology coming with this. So if you have this C2T symmetric system, there is no local constraint on the edge to have anything gapless. So even though the Wilson loop has a gapless state, this red and green state, the edge is not C2T invariant locally. So the edge is what's that? The edge is gapped. However, in this non-trivial phase, you will find a pair of corner modes, which are, again, you can derive it by similar argument as before, where we say, we have this gapped. If you start with a quantum spin Hall state and you introduce the time reversal breaking, but C2T symmetric perturbation, you can gap the edge here, you can gap the edge here, but here you have M. Here you have to have minus M. That's coming from the representation theory of the C2T, and at the domain wall there's a corner state, similar to the case of this A3 plus mirror model that I just discussed previously. Okay, good. Time to move on to delicate topology. And so this was the example for fragile topology. And so in this sense, this was strong, this is fragile. Now comes number 3, delicate. Just want to make sure you get the right reference if you want to read up on this. This is the place to do that. 126.404. So the point is that you can remove this obstruction. I'll get back to Daniel's question. You can remove the obstruction of exponentially localizing symmetric Wannier functions and trivialize by adding orbitals, atomic limits, even to empty bands. Which sounds a little bit funny because all the time we've been talking about the occupied subspace and the topology of that, and I don't know, nobody ever cared about what's above it. But I'll just show you a quick example as to why these actually can matter for defining certain types of topology. Before that, Daniel's question, what would happen for a circular sample? Good question. So you would have still 2 modes here. However, and their location is determined by boundary conditions. So they'll for sure be somewhere, but you know the direction is basically a non-universal thing, nothing that you can deduce from the bulk. The other thing is that these modes are not necessarily exponentially localized anymore. It could be that they have they could have along the edge. They could have an algebraic decay potentially. Yeah. But in principle, the modes as a spectrum in a spectrum, they're still there, and the thermodynamic limit they'll be degenerate by C2T. Thanks. All right. So go back to delicate topology. What's an example? There we go at 2D system with mirror symmetry. And let's say my is equal to sigma z. So what I have in mind is a system with, you know, it's y and x direction. I'm just drawing one unit cell. And in this unit cell, I'm putting 2 orbitals. One is an s orbital and one is a p orbital, right? With respect to the z direction. So I have 2 bands. And they have opposite mirror eigenvalue. That's what this mirror symmetry is telling me. And now I invite you to think how this Hamiltonian could look and the eigenstates. And the point is, if this is a 2-band system, then there's one occupied and one empty band, and in the Brillouin zone, I have now the mirror invariant lines, pi and 0 for ky, and on these lines, this line here and this line here, there is something special happening, namely the eigenstates of the system are constant. They don't depend on kx, and that's just because I have only you know, the Hamiltonian has to commute with sigma z, and it's only a 2x2 matrix. So eigenstates along these lines are constants. The Hamiltonian can still have a kx dependence in that there can be a dispersion of the band, but again, along this line, the eigenstate is going to be the same. And what this implies is that usually I think of the whole Brillouin zone as a torus because I can compactify it due to the periodic boundary conditions. I know that the eigenstate at k and k plus 2 pi is going to be the same. But now I know that the eigenstate at k equals to 0, ky equals to 0, and pi is going to be the same. So I can compactify actually half of the Brillouin zone. So I can define the Chern number on half of the Brillouin zone. So I can look at the system where the Chern number is +1 in one half and -1 in the other half. But the Chern number of half of the Brillouin zone is well defined. So Chern number of half Brillouin zone is well defined, and that's because of this. So of course, in most simple systems, it will be 0, but I can imagine systems where it's not the case. And so this is a topological invariant for this delicate system. And you saw that for my argument, it was quite crucial that the mirror eigenvalues are that the mirror eigenvalues are or that these eigenstates are constant. And so for instance, if I look at as a function of ky, then these bands would have mirror eigenvalue, let's say -1 here and -1 here. The upper band would have +1 here, +1 here. So these are the mirror eigenvalues. Note that we don't expect them to switch here, but something very interesting is going on with the states in the middle because they produce this Chern number. Yeah. Yet the mirror eigenvalues should stay the same as you go across across this Brillouin zone. And now you see that if I add to the conduction band another band which has mirror eigenvalue -1, for instance, now I can start to mix mixing prevents or yeah, basically makes eigenstates different at ky equals to 0 and pi in general. So then this, the whole foundation of this delicate topology goes through the out the window. This is just one example of such a delicate topological system. In this reference that I gave, we actually looked at the 3-dimensional system, Hopf insulator. You can also look at 1-dimensional systems. So just the principle is always the same, or not always, but oftentimes the same, that there are some symmetry constraints which make the eigenstates of the occupied bands constant in a subset of the Brillouin zone. And you can use that to define topological invariants that are otherwise not defined. So maybe let me wrap up this delicate and fragile perspectives with a Wannier state picture. On the level of the delicate, that's actually still a conjecture. So if you have a stable topology and you have your atoms, then no matter what you do, your Wannier eigenstates are very extended, so not exponentially localizable. If you have a fragile topological system, then the picture, if you impose the symmetry on the Wannier state, looks very similar. So note, for instance, that I put a one-year state here at the high symmetry position. But actually, so there's one option to evade that. Actually, even for stable topology, sorry, there's the option of evading that if you kind of do away with the symmetry, yeah, of symmetry. But with fragile topology, you can actually, when you introduce extra orbitals that are localized somewhere in your system as additional orbitals, then so they're not exponentially localizable, but plus extra orbitals, they become exponentially localizable. I'll take the question in just a moment. And then there's the delicate case. And what we find there is something that we call multicellularity. And that's still a conjecture, let's say. So what we find there is that the one-year states are exponentially localizable of such a delicate system. However, they can never be deformed to only have support in one unit cell. So exponentially localizable, but spread over several unit cells. So that's multicellular. So that's different from the other cases. And of course, when I say spreads over several unit cells, I mean really this in the sense of a deformation. Yeah, usually a one-year state anyway spreads over several unit cells, but you could deform your Hamiltonian adiabatically in such a way that you get a delta function if it's exponentially localized to begin with. What I'm saying here is you cannot keep the same number of bands and the symmetries, deform your Hamiltonian so that your one-year state's only sitting in one unit cell or on one atom, essentially. It always has to sit on two. All right. Now let's go through the question. Is it changing the shape of the one-year function when the empty states are adding? Yeah. I mean, not by adding the state to the Hilbert space, but once you couple that added state that you have available, keeping the same number of occupied bands, the same filling, adding an empty state, coupling it into the system, that will allow you to change the one-year wave function, yeah, of the occupied bands. That's question number one done. Is there a bulk boundary correspondence for this delicate Chern number? So in general, for these delicate phases, I think I cannot give you a complete answer. In the case of the Hopf insulator, there are definitely boundary states, but it's quite subtle. One has to distinguish cases where the boundary is sharp and non-sharp, because generically, the feature that you have something spreading over two unit cells is lost the moment you have broken translation of symmetry. So I would say that bulk boundary correspondence for delicate systems is to some extent still an open problem. Yeah. And Mikael, for delicate types, the one-year function lattice has still the same periodicity as the real lattice. Yes, okay, good question. So maybe, from my picture, you would assume that you have only twice fewer one-year states than you have lattice sites. But this thing is now, there are one-year states in every unit cell as before. So the next one would look like this and so on. They are overlapping, but they can be orthogonal in their internal structure, yeah, because every unit cell has already 2 degrees of freedom and so forth. So yeah, good question, but still one per unit cell. Good. So now it's time for me to wrap up. And I think I promised a little bit too much for these lectures. Maybe I also promised you to give an introduction to non-Hermitian topology, which I entirely didn't get to. I think there are several good reviews on this topic already. If you're interested, I can point you to one or two and do that in the Slack channel, for instance. Let me just say two words that the non-Hermitian topology is basically the idea that you look at systems where a Hamiltonian or some sort of a matrix that encodes locality, so where you can build a system with some local couplings or so, has a spectrum that can be topologically characterized. So it doesn't need to be literally a Hamiltonian of the system, because a Hamiltonian should be Hermitian, but it could be a Green's function, it could be some sort of a response function of a classical system or whatever. But something where you have a sense of locally coupling degrees of freedom and taking a thermodynamic limit, and you want to know about the thermodynamically large systems, some topological information. So that's something that's been really looked at intensely in the last couple of years. And it's a little bit sad that I didn't get to it, but yeah, just know that there's a lot of development in the topology of these or in these topological classifications, and it's quite interesting because a lot of our intuition breaks down, since these non-Hermitian systems, for instance, they are very sensitive to boundary conditions. Perturbation theory doesn't work quite the way it does, and topology cannot be only encoded in the eigenstates, as it's the case here, but it can also be encoded in the eigenvalues. So if you have complex eigenvalues, as a non-Hermitian matrix in general does, then you can have a binding of that eigenvalue in the complex plane without anything interesting happening to the eigenstate, and that could be topological. Is it possible to use a Wilson loop formalism to detect delicate topology? Yeah, yes, yeah. For instance, the one that I showed with the Chern number plus or minus 1, we can do that. Yeah, the Wilson loop would show exactly this Chern flow. So it's actually a good tool. Also in these 3D examples that we study in the paper I gave, it's a good tool to look at the Wilson loop spectrum. Yes. Okay, good. I should stop here and ask maybe for more last questions from anyone, or comments or anything.
Let me check if there are questions in the Slack channel.
There is one. I see you say I should just answer it. No, that's from yesterday though.
Yeah. Isidora.
Is it correct that only after choosing a smooth gauge, the eigenvectors of the Wilson loop correspond to maximally localized Fourier functions along one direction? Yeah, smooth gauge in that one direction, yes. There are 5 replies to that. Let's see what people. Okay, maybe I should do that in peace and quiet later. Yeah, that seems to be like a. Okay, okay. I guess I'll go into that later. Here's a question. Delicate topology could be characterized by quantum spin Hall or anomalous Hall effect. No. That would be nice. I would love to know what actually is a good way to measure delicate topology, or what it would be observable. The quantum spin Hall, anomalous Hall, conductivity, unfortunately, they vanish for these systems. Yeah. Is the delicate topology one-year picture, right? In the delicate topology one-year picture, is there any restriction on the spread of the wave function, in the sense of, do they need to be in contiguous unit cells or not really? No, there's no. I don't think there is a strict sense in which they need to be like in the neighboring unit cells or something. The statement, I don't think I can give a complete answer, but no, there's no simple statement I can make. It could depend on the case as well, how many unit cells they go through, but usually I think the cases that we studied are in neighboring unit cells. But I don't think I can give a very insightful answer to this question. Yeah.
Okay, seems there are no further questions. So yeah, let's just stop here.
All right, good.
Thank you, Titus. Thank you for this beautiful talk.